Hi, welcome to lecture 14 of ECE 1 for 1. In this lecture, we will talk about convolutional codes. So from the previous lecture, we talked about cyclic codes, and cyclic codes are basically a form of linear block codes. And linear block codes actually are somewhat a form of convolutional codes. So we're getting more general here. Specifically, linear block codes are convolutional codes without memory, or a memory length equal to, 0, rather, not 1. Okay, let me delete that. Memory length equal to 0. So a convolutional code takes block codes, linear block codes, to the next level, right, by having some form of memory. So that's why convolutional codes can be described as block codes with memory, and it uses memory to generate a code word. In effect, your generator matrix also contains some form of memory, but we don't really use the generator matrix to generate a convolutional code, as you will see in the succeeding part of the lecture. Generally, the code word is a function of the current message and the state of your machine. So we define a convolutional code with 3 parameters, n, k, and m. N is the number of code word bits. K is the number of message bits. And m pertains to the memory length. Okay? For example, first let's illustrate that with an example. For example, let's say the number of message bits is equal to 1, the number of code word bits is 3. And this is the block diagram that implements a convolutional code where the message bit is 1 and the code word bits, or the code word length, is equal to 3. Okay. It uses shift registers, as you see here. These are shift registers to create memory in the convolutional code. Basically, using these shift registers, then just clear the clutter. In this shift register, if this is the kth bit message bit, then the output right here is the k minus 1th message bit, and this will be the k minus 2 message bit. Okay, so the message bit 2 symbols ago, or 2 bits ago, the message bit 1 bit ago, and it turns out that your 3 code word bits, so this is the kth code word bit for 1, here's for 2, here's for 3. For 1, it's equal to your current input, as you see here, and that's it. Your second one is dependent on the current input and the k minus 1, the previous input right here. And the third one is dependent on all 3, as you see right here. Okay? And that's how you generate your convolutional code. In this example, the memory of your convolutional code is m is equal to 2 due to the presence of 2 shift registers which are connected in succession. Okay. And the output has 3 bits. So you form them by multiplexing these 3 bits and forming a chain together. There you go. This will be the sequence of your output code word. Okay. Another example is this. For this one, the memory is equal to 1. Okay, since you may have 2 shift registers in the block diagram, but they are not connected in succession, leaving your memory amounting to 1. So you only depend on the past input right here, as you see here. There you go. If I add a shift register here, in succession, then you're already dependent on the past two inputs, which makes memory equal to 2. But in this case, you're not doing that. Okay, so let me just delete that. Okay, there you go. Oops. Okay. So in this case, you have 2 message bits and 3 code word bits. Therefore, this is a 3-to-1 convolutional code. Okay. So how do you characterize its generator matrix? Since the convolutional codes have memory, your convolutional code or generator matrix will also have memory. Take for example the 312 code that you saw earlier. That's this one, as you see on your screen right now. If your message is an impulse function, let's say it's 1 then all zeros, there you go. Your output will also, you will have an output that corresponds to this. Okay? C of 1 is only dependent on the current input, so its next 2 inputs will be 0 right here. C of 2 here is dependent on current and 1 previous input, so you'll have 1 1 0, and the third will be dependent on all 3 the current input rather in the past 2 outputs, the past 2 inputs, so you'll have 1 1 1. Okay? And these are the impulse responses per output. With that, you can already form your generator matrices. So G1 will depend on the output of C1, G2 will depend on the output of C2, G3 for C3. And for a given message sequence, then you'll be able to get your output by convolving the generator matrices with the message sequence. Okay, that's why it's a convolutional code. You have to perform convolution. Okay, so for example, for a 3-to-1 convolutional code that you saw earlier, let's say you have this B of 1 right here. You have an impulse response. An impulse input rather. The output of C of 1, let's say this is all 0. The output of C of 1 will become, okay, your C of 1 is dependent on B1 of k minus 1 right here. It's dependent on B2 of k. And since we don't care about B2 of k, then let's just ignore the terms with B2. So it's these 2 terms connected to C of 1 are dependent on B2, so we will ignore them. It will only depend on the past input of your first message bit. So the C of 1 that will arise from the impulse response right here is equal to 0 1. So that will be the first row of the first generator matrix. Now if there's an impulse response on the other side, so let's say you have an impulse response on B2, so this will all be 0, B1 will all be 0, B2 will be 1, then followed by zeros. Okay, so the output C1 right here will now be 1 1, as it is dependent on the current input B2 and the past 1 input of B2. So you'll have a response 1 1. That will be the second row of your first generator matrix. The others can be determined in the same way. So that's how you get the generator matrix of a convolutional code. Now, since your convolutional code has memory, then let me reintroduce your state diagram and trellis diagram. If you have memory, you're a finite state machine. A finite state machine will have a state diagram and a trellis diagram rather. And this will help us identify the behavior of your convolutional code. Okay? So the maximum number of states of a convolutional code is dependent on the number of message bits and the memory. Okay? So for, let's say if you have L shift registers and 1 bit, then the number of states is equal to 2 to the L. Okay? So example, you draw the state diagram of the 212 convolutional code that you see right here. Okay? So how do you do that? Well, you use a truth table. So a truth table will be a much easier way to determine the state diagram. So first determine, well, the equations, the relationship of your outputs to your inputs. Then we use them for a truth table. Since the memory of your system is 2, then you need to use 3 inputs. That would be the past 2 inputs and the current input. So they will be the members of your truth table. They will define the different outputs and the different states. So if, okay, let me just clear the clutter. Okay, so for the first state 0, 0, that is defined by this one, it will transition to 0, 0 defined by this one. From here, you start at 0, 1 defined by this one. Will transition to 0, 0 defined by this one, and so on and so forth. Okay. So with that, you can form your state transition diagram. So you start at 0, 0, then you transition to 0, 0. Transition to 0, 0 when you have a 0 input right here, which results into a 0, 0, 0 output. There you go. From 0, 1, let's say it's right here, you transition to 0, 0 if you have a 0 input and an output of 0, 0, 1. And you do that for every state transition that you see here. It will result into a state diagram that looks like this. This is the state diagram of your 312 code example that I've shown you earlier. And from here, you can actually create the trellis diagram. So for a convolutional code, if you've noticed your state diagram, it always starts, or it always has this loop right here. A good convolutional code will always have a self loop at the 0, 0 state. That would mean that if your input is always 0, your convolutional code will always return to the 0, 0 state. That's why when you look at the trellis diagram, you always start at the 0, 0 state. Okay? So, if you look at the trellis diagram, then here from 0, 0, you can transition to 1, 0 or 0, 0. And they have the corresponding outputs labeled here. From 0, 1, you can transition to, from 1, 0, you can transition to 0, 1 and 1, 1. Okay? And they have the corresponding outputs you see right here. Okay? And as you can see, after 2 transitions from here, your trellis enters steady state. Okay? The transitions that you see from this time from here to here, you can see all the possible transitions in your finite state machine. So this is your trellis diagram. So just some notes, your convolutional code enables transmissions to approach the channel capacity. If you want to be close to the theoretical maximum as postulated or as proven by Shannon, then you need to use convolutional codes. In general, your convolutional codes has at least 2 terminal states, an all 0 state and an all 1 state. So that's an example here. If your inputs are all 0, it will always converge to 0, 0. If your inputs are all 1, it will always converge to the state 1, 1. Okay. And in practice, the convolutional code will always reset to the 0 state after transmission. This ensures that any new transmission starts at the all 0 state. That's why if you look at the trellis, you always start at the 0, 0 state. Okay. And this is done by appending MK zeros to the input sequence. So if you have an input sequence, the convolutional encoder will always append MK zeros after each transmission. Right? By this practice, your decoding becomes easier, becomes the initial state, because the initial state is known. Example, trace the trellis path of the input sequence 10011. Okay, so what will be the trellis path? You start from 0, 0, you have an input 1, oops. You go in this, you transition through this path. An input 0 will transition to this. Another input 0 will transition to this. Okay, and input 1 will transition to this. Input 1 will transition to this. So let's see the path in the trellis. There you go. So an input 1 will transition here, input 0 will transition here, input 0 transition here, input 1 transition here, 1 here. Okay, and then both zeros, you append 2 zeros to make sure that your convolutional code will reset to the original state. And the resulting code word sequence is equal to this one. Okay, so that's the end of part 1 of lecture 14. If you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.